And what we have here is some of the specifications that you need. You can consider typical specifications when you're constructing marginal bands, and they serve a number of purposes: preventing floodwater from entering surrounding area, which may be submerged or waterlogged. It maintains floodwaters within a specified section. The various hydraulics, and also try to come up with design parameters or, design aspects of this kind of a structure. When you are looking for your attachment, I don't know whether you are going to go after FIFIA. Maybe people can think about if you can go to that by wear and barrage in Galana Kalalu and see what will happen. If you can get an opportunity there and get first-hand information, even interact with design of the complete structure. Here we are only going to limit ourselves to the wear or a barrage, and we are not even going to do the structural design, but basically calculating pressures at various points. Yes, and I want us to take a break so that when we come back, we can look at generally these causes of failure are expected, because when we come now to the design part, we want to design so that we can minimize the effect that causes this failure. So before we go, I want to check who is in. So Boris Obuya and Victor Kariuki, where are you? Boris Obuya, Victor Kariuki, tuko pamoja kweli? Victor Kariuki, huyo amelala. It was
I'm present.
You are present. So why aren't you? Anyway, let us meet at 8:20 or even 8:30, so that we can now come and look at the various sources of failure and so forth and so on. Okay, we are back, and I start with taking a poll. I just want to see that we are all here. We have check. Who has? We have a number of people: James Joroge, Tanya Adhiambo, Victor Kangor. Anyway, let us continue. So we are now to look at the causes of failure of the structure. One thing that should be at the back of our minds, we make weirs and barrages in floodplains on porous media. So they are founded, or rather, when we say they are founded on alluvial soils, when we say they are founded, that is, the foundation is alluvium. Now, one characteristics of these kind of soils is that they are easily eroded when we have very high velocities as the water passes over the structures. And again, the failures, and again, we have a lot of seepage beneath those structures. There are two broad categories of the modes of failure modes of failure of weirs and barrages. One is due to subsurface flow, and secondly, due to surface flow. And before I continue, I will just list and generally explain the subsurface flow and the surface flow failures. One, due to subsurface flow, if you remember soil mechanics, the effective pressure at any point within a soil layer is a function of the pore water pressure and the matrix pressure. The pore water pressure and the matrix pressure. Now, pore water pressure, and in soil mechanics, we usually consider, when we are talking about pore water pressure, we are talking about saturated conditions. In this kind of a scenario, we also expect saturated conditions. Why? Because we are talking about the ground or a layer of soil below the structure where a river passes on top. So chances are that you have saturated conditions below the structure. So this pore water pressure, or the total effective pressure, determines if a particular foundation is able to carry the overburden. In this particular case, we have added an overburden in terms of the structure. Most of the time, this structure is concrete, so you have added another weight of the concrete on top of the existing ground structure. No, again, these pressures, because now under equilibrium conditions, you may not have a lot of problems, but now when the water is moving, you have some kind of a hydraulic gradient developing between the upstream and the downstream, so that you can have flow beneath. So these pressures can be high, very high, and thereby causing destabilization above. Again, these pressures can be too high, such that they destabilize the soils and transport soil particles from the upstream, from beneath, and the soils exit in the downstream part of the structure. And in soil mechanics, there is something we called, we called something like quicksand piping. They are usually arise due to excessive pore water pressures above the weight of the pressure or the weight of the soil particles that are beneath. So the concept of piping, the concept of quicksand, the quicksand effect, that is one of the kind of failures due to subsurface. Those are the two kind of failures due to the subsurface flow. So one, you can have poor water pressures causing very high uplift pressures, so that you are going to have rupture of the structure or piping and such kind of a thing. Then we have due to surface flow, and I mentioned it a little bit. When I was talking about the water flowing above the weir. Then when it is flowing on the slope of the downstream glacis of the weir, it is going to tend to flow on a very high velocity, kind of supercritical flow conditions. But when it gets to now the riverbed in the downstream, you get kind of subcritical flow conditions, very low control flow conditions. And when you have a supercritical flow flowing into a subcritical flow, you have now a hydraulic jump developing at some point. And in most cases, in this kind of the scenario of weirs and barrages, the hydraulic jump mostly forms on the downstream glacis or the downstream slope of the weir. Hydraulic jumps have suction pressures. Hydraulic jumps usually have suction pressures. Another thing about surface flow is erosion, bed erosion, basically. And normally we have, when you're given a specific type of soil, there is a maximum depth of erosion that can occur. For example, if you have a silt that has this type of characteristics, it has particles with a certain D50, a certain mean diameter, you'll find that the maximum erosion that can happen in that particular point is maybe, let's say, 1.5 meters, 2.5 meters, and what have you. So those are the four kind of scenarios we are going to be checking. And because once we check this, then we will further look at the design aspects that follow. So first, we have the failure to subsurface flow, and we have failure by piping or undermining. And like I have already explained, you get water from the upstream side continuously percolating through the bottom of the foundation and emerging at the downstream end of the weir or barrage flow. Now, remember, for any flow of fluid to occur, and this is either from fluid mechanics or hydraulics, you have to have a kind of gradient developing. You cannot have a flow of water when you do not have a gradient developing. When you do not have gradient, remember, water flows due to the mechanical energy. That flow of fluids is controlled by the mechanical energy that controls, that is differences in mechanical energy. And I want to, before I go further, I want to show what I'm talking about. Yes, so I can use one of these. So you look at before, even in a natural channel, water follows a certain slope, and water flows from a region of high energy to a region of low energy. This energy, which is usually called the mechanical energy, can be described by the Bernoulli equation. And in that Bernoulli equation, we have three terms. We have the kinetic term, the gravitational term, and the elastic, elastic energy term. The elastic energy one is the one that we calculate, the elastic pressure term, the one that is defined by the density and depth of the fluid, the rho GH. The kinetic energy is controlled by, is the one that is usually described by the velocity caused by the velocity of flow. And then we have the gravitational one, or the potential one, that is usually related to the elevation of that fluid. So now, in this particular case, in the upstream side, this is the upstream side, and then this is the downstream side. You are going to have a very high water level in the upstream and in the downstream. And if I was to draw the tentative water level in the downstream, once the water flows above, you are going to have such kind of a water level. So you are going to have, if you calculate now that mechanical energy, or normally, and you remember in the mechanical energy can be expressed in terms of water potential or energy potential or hydraulic head. So if you were now to change it into hydraulic head, and the hydraulic head is basically the elevation of the water, so you are going to have the difference, a very high hydraulic head in the upstream and a low hydraulic head in the downstream. And because of that, you have some kind of hydraulic head gradient. And that is what causes now the water to seep beneath. We have high head here, we have low head, and the water will have a tendency to flow. It cannot flow through the weir, so it flows through the porous beneath, the porous media beneath. So we go back, the piping and undermining, we are talking about the water in the upstream will continuously percolate. Why? Because there is that difference in hydraulic head, and we are going to have, constant percolation beneath. And that water emerges downstream end of the weir or barrage. So the force percolating the water, this force percolating the water can remove soil particles by squaring at a point of emergence. So when the water emerges at the downstream, if the forces are so high, you can have some erosion of the particles below. So, and we shall see later, the essence is to ensure that the forces that are beneath do not have the energy, are not enough to carry those soil particles. So as a process of this removal of soil particles goes on, you have kind of a depression forming, which extends backwards. No, we will see all this in detail a little bit later. So let me not even bother to explain much, because we'll see it later, and I'll be able to explain using a diagram. So this depression, you have kind of a pipe forming from the downstream end. So the erosion starts from the downstream part. So some particles are eroded away, and then we have the continued erosion through that particular kind of a section, forming some kind of a pipe that propagates from downstream to the upstream. And this phenomenon is called piping by undermining, failure by undermining or piping. So that piping can extend all the way until it gets to a point, to the upstream part, or even to a point now where your barrage does not have a foundation below. It doesn't have a foundation below, and your structure is going to fail because of that. Then we have failure by direct uplift, and this percolating water exerts an upward pressure. It exerts an upward pressure on the foundation of the weir. And if this is not counterbalanced by self-weight of the structure can fail by rupture. Then we have failure due to surface flow. One is by the hydraulic jump I mentioned. And this one I explained is because we have water flowing at a very high velocity as it flows in the downstream slope of the weir, but then it comes and meets a low flowing water and even the slope is flat. That is what causes the hydraulic jump. And I mentioned briefly that the hydraulic jump causes suction pressure or negative pressure. I know you have done hydraulic jumps in hydraulics. And so once you do the hydraulic jump and you can easily now calculate the uplift pressures that are associated with the hydraulic jump. In this particular course, we will not go into those details, but they are usually very important when you are doing the weir of the barrage. You have to calculate the position of the hydraulic jump and make sure you design to counteract that effect. So if the thickness of the impervious floor is insufficient, then the structure is going to fail by rupture. Then again, the second way you expect failure due to surface flow is by squaring, that is erosion. Basically, when water is flowing in a porous media in unconsolidated soils, you're going to have erosion. When you have erosion and exposing your foundation, you're going to have a structure that is not lying on any foundation at all, and it is going to fail. So what are the design aspects, therefore? For the subsurface flow, we have a number of things. We have a number of provisions, and also for the surface flow, we have a number of provisions. One, for the subsurface flow, we want to keep quiet. You have a question? Anyone with a question, you can just make a comment. We are almost, I will just mention the design aspects. We are going to finish at that. And then, because once we now come up with the design aspects, we will go to theories that have been used to provide for that. But we can have a discussion. You have any question, you can ask. Keep quiet? No?
No, I'm good.
Great. We have Arnold at Asitiba. Question? You raised your hand. Now, Boris Obuya, and there is another person who has joined with call. With that is William Wako. I mentioned before last time that you join with microphone. I just chose today. I didn't want to. It is very early in the morning. I don't want to cause unnecessary stuff. So when it comes to the subsurface flow, the structure, one, should be designed as the piping failure does not occur due to subsurface flow. So normally what happens, and we will see later, much later during some of the design principles or design theories, that a downstream pile must be provided to reduce the exit gradient and to prevent piping. So in the downstream part of the barrage, you provide a pile, downstream pile. Secondly, we provide an impervious floor of adequate length to increase the path of percolation. I have showed we develop some kind of hydraulic head difference between the upstream and the downstream. So if you have the distance between the two water levels being shorter, you are going to have a very high hydraulic gradient. If you make the difference between the upstream water level and the downstream water level to be longer, you are going to have a lower hydraulic head gradient. So one of the design aspects is to make the flow of the barrage very, very long, so that the path of flow of water is also long. Again, the seepage path is increased by providing piles and impervious floor to reduce the uplift. So you find that in addition to the downstream pile, and when I talk about a pile, I'm talking about a wall concrete wall that runs from one side of the riverbed to the other side of the riverbed in the foundation. So you have another pile, maybe somewhere in the middle, another one in the upstream, just to continue increasing the length of flow of the water. And we'll see how that happens using when we start discussing the theories. Then we have the thickness of flow should be sufficient to resist the uplift pressure due to subsurface flow. So you need to have a minimum thickness, a minimum design thickness. And there are also ways to do that. Then finally, you need to provide a suitably graded inverted filter at the downstream end of the impervious flow to check the migration of soil particles along with the water. So you prevent the soils from leaving the subsurface by providing a filter. And here we are talking about an inverted filter, just the same like we have in slow sand filters or rapid sand filters. But now in this case, you invert it such that the gravel is on top and then the graded sand is at the bottom. So you provide it at the bottom, at the downstream part where you expect to have the particles to leave, to flow out of the subsurface. Then we have surface failure to design considerations related to surface flow. One, you provide piles or cut-off walls at the upstream and downstream ends of the impervious flow up to the maximum score level. And I mentioned it a little bit. I said for any soil particle and consolidated particle, there is a maximum expected score depth. And even when you're doing bridge design, you're doing design of structures that exist in such kind of areas, you realize there is that maximum score level. And so your the piles that you're going to construct have to be at least that depth. Two, you need launching aprons at the upstream and downstream ends to provide a cover to the main structure against score. So first you provide, let's say like a concrete structure or whatever kind of structure, just maybe a wall sloping from the structure, so that erosion, when we have erosion, it does not get to the piles of the barrage and weir. We will not do launching aprons, we will not do this, but if we were to do everything, we would never finish this course. We would only do, like I've said before, we would only concentrate on designing weirs and barrages. Then we need to provide a device in the downstream to dissipate energy. What normally is done is you design for a hydraulic jump. You design specifically for a hydraulic jump. So that I need a hydraulic jump here, and you design for it. Further, you provide an additional thickness at the point where the hydraulic jump is formed to counterbalance the suction pressure. And you will see in most of the figures that we are going to see, the downstream wall of a weir or a barrage is usually thicker. It is usually thicker than elsewhere. Then the floor is constructed as a monolithic structure to develop bending resistant or beam action to resist structure pressure. The same way we do beams and columns, most of the time when we are making them, when you're making a structure of a building, a skeleton of a building, a skeleton of columns and beams, the idea is to make it as a monolithic structure so that you create some kind of bending resistance, beam action. And you notice, like, even when you're doing buildings, you are going to have columns, but you have to connect them somewhere so that it is a continuous, it is one thing. So the network of beams and columns is usually a monolithic structure. So that is the essence here. When you're making your weir and barrage, in order to increase the bending resistance, you make it as one structure, so that the bed, the piles, the barrage itself, the superstructure, all of them are just one single structure. So now, when we come next week, I think it should be Monday, we should look at now the theories that have been applied to in order to design for the various design aspects that we have stated. Any question or feedback or anything that we can end our class today? Any question? And I want to call another poll so that we can make our final class attendance. Any question? Any comment? Okay, so we meet on Monday. I don't know whether it is Monday or it is whichever day. So let us meet on that day to continue with our course. I stated, did I state that we were going to do design exercises? Because already I should be providing my first assignment. And it will be, we need to do different wares and configurations and divide ourselves into groups so that we can be able to do them. Okay.